Hi, I'm Donghyun Lim, a PhD student from KAIST. This is a collaborative work with Svetlana Selivanova and Martin Ziegler. This work was supported by the National Research Foundation of Korea and by the International Research and Development Program of the Korean Ministry of Science and ICT and by the NRF Brainpool Program. We particularly thank Akitoshi Kawamura and Florian Steinberg for helpful advice and feedback. Complexity and coding theory of Hilbert spaces. Let me start the talk. The structure of the talk is as follows. First, I'm going to give you an introduction, the background of this research. Then I'm going to define what the large L21 space is and talk about its representation and properties. In a similar manner, I'm going to define the small L21 space and talk about its representation and properties. Finally, we will look at the perspective of this work. So, this work is about the complexity and coding theory of Hilbert spaces, where it is known that there is only one infinite-dimensional separable Hilbert space up to isomorphism. This will be our main object of study. As an example, large L2 is an infinite-dimensional separable Hilbert space. It is the space of complex-valued functions defined on the unit interval that are square integrable. Its inner product is defined as an integration from 0 to 1. In this space, more mathematically precisely, this is a quotient space. The two functions, they are as functions, maybe they are different, but if they are equal almost everywhere, then they are considered identical. In this space has this orthonormal basis, and this orthonormal basis provides us another way to encode this space as a representation. Roughly, entropy is the method of measuring the size of a space. For a compact space, you could always cover the space by finitely many number of balls. But how many finite balls do we need? Entropy is about this idea. Given some n, F can be covered by this amount of balls with this diameter. So given a diameter, how many balls do we need to cover the space? As in this diagram, as you can see, as the radius of the ball gets smaller and smaller, you need more and more balls to cover the space. And this is a function of this radius. We could also consider this 2 to the minus n radius, and this is a function as the ball size gets smaller, the number of balls required to cover the space gets increased. So this is a growing function. For example, this unit interval has identical entropy. If you halve the size of the if the size of the radius gets halved, you need twice more balls to cover this space. But for example, some more complicated spaces, like the set of all Lipschitz functions from unit interval to unit interval, then this space has exponential entropy. Entropy is a way of measuring the size, how complicated it is, or the complexity of the size of the space. So for this complex space, this entropy is more fast growing than the simpler space. So consider these diagrams as functions. Then some of them, these 8 functions are continuous functions, and these 2 functions are discontinuous functions. But even among those continuous functions, these 2 are more continuous, and these 2 are continuous but almost discontinuous. So even among these continuous functions, there's a difference. A modulus of continuity is a function defined as a natural numbers to natural numbers, measuring how continuous or how discontinuous a function f is if defined by this equation and because it is defined as a function from natural numbers to natural numbers, we are usually interested in its asymptotic growth. But there is a relation between modulus of continuity and entropy. For a surjective function and its modulus, with eta of x and eta of y being the entropy of x and y respectively, this equation holds. So entropy works kind of as a lower bound for modulus of continuity. So in many cases, we want to find an f with asymptotically small modulus, and this lemma establishes a lower bound. So to introduce the computability or complexity concept of a general space for the topological space or metric space, we need the idea of encoding or representation. Viral uses this style of representation, a partial surjection from counter space to infinite length bit strings to some space of interest. And Kawamura in 2012 uses a different style of representation. Here the base space is a string functions, the set of all string functions of this type. And as a representation, it is a partial surjection from a string function to the space, and an element is encoded not as a binary sequence but as a string function. Here, in our case, we use a bit different style of representation. Here there's this star and there's no star here. This is not just a not a string function, but a string predicate. And here we define metric D on the domain in this way. We encode an element of X using this string predicate. The distance is defined in a way that if psi and phi are cross, if and only if they agree on all strings up to some length. So I want to give you an example of a representation using this base space of string predicates. This is a representation of Lipschitz function, one Lipschitz function from unit interval to unit interval. And this Lipschitz space of Lipschitz function is compact according to Azar-Ascoli, and therefore our previous definitions like entropy is applied to this space. And this standard representation has a linear modulus. This standard representation is defined in a way that this is the domain and codomain, and any string predicate is mapped to the function f if and only if just read this following. And here the important thing is there are parameters n, j, and a, and n and j are encoded in unary and a is encoded in binary. N is the precision parameter, and j is because this is a string predicate, not string function. The answer is just 1 or 0. We need this j to encode the information, and this is the input value to this function f. And this space has a linear modulus because this a is represented in binary. If it were in unary, this wouldn't have a linear modulus. And if n and j are encoded in unary, but if it were encoded in binary, there will be some the polynomial time computability theoretic properties will be broken. So it is a must to encode n as a unary and j as binary, j also as unary and a as binary. This modulus is asymptotically optimal by Steinberg's lemma, since both this domain and codomain have exponential entropy. But with respect to this representation, the application or functional is polynomial-time computable, shown by Kawamura in 2012. But this is actually the precise characterization of any representation of this. That is, a representation delta of the space of Lipschitz functions is polytime reducible to the standard representation if and only if it makes the application or functional polynomial-time computable. So we went over the introduction or the overview of the talk, and I'm going to define and introduce the L2-1 space. L2-1 is basically a compact subset of L2. So it is a space of complex valued functions defined on unit interval where the norm of each element is less than or equal to 1, and norm is defined this way, and there's this additional condition. This tau of epsilon is a cyclic shift operator. It is using equation defined this way, but there's this function, and if you shift it a little bit, then there's the difference in this area, and the meaning of this inequality is this difference, this red lined area is small enough. So this is the definition of L2-1 function, and its compactness is proved by Freshev-Kolmogorov. We consider a representation of L2-1, and this we call piecewise representation. The piecewise representation, the domain is the set of string predicates, and here as you see in this diagram, what the encoding encodes is the value, but the averaged value defined by integration, and with respect to some precision parameter and the location of this interval. So there are three parameters as before: n, j, and a. J this we need because this is a string predicate, and n is the precision parameter, and a is the parameter for this location, and only this one is encoded in binary. And the average, as you see from this equation, is defined using integration. In this space L2-1, this is a compact space, compact subset of L2 space. This has this amount of entropy, and this base space has also this amount of entropy. This and this both are exponential, and piecewise representation has linear modulus, and we say this is optimal. We know this is optimal by Steinberg's lemma. So there is this theorem. Under piecewise representation, the functional given f, we need to calculate the area under this curve by integration. It's not polynomial time but exponential time computable. This being exponential time computable is obvious because we query this value in this interval and this value in another interval, and then and so on for every interval. But there are exponentially many intervals, so this, and adding them up, this takes exponential time. But the reason this is not polynomial time computable is that basically you have to access exponentially many intervals, and this proof can be made formal by perturbation argument. And we conjecture that under piecewise representation, the pointwise operator is pointwise operator of taking multiplication and square root is polynomial time computable. So consider an arbitrary function from L to 1 space. And for each interval piecewisely we can calculate the average by integration. And this is a piecewise constant approximation in some sense, and this was linearly interpolated one. But this space of L to 1 is not closed under piecewise constant approximation. So even though f is in this space, this piecewise constant approximation may not be contained in the space. But this piecewise linear approximation or linear interpolation, if you go through this, the approximated function will still be contained in this L2-1 space. So this has been the explanation for L2-1 space, and I'm going to talk about this time small L2-1 space. Small L2-1 is the space of complex value sequences defined on integers. It satisfies this property, so it's square summable with the norm smaller than or equal to 1, or this also satisfies the same equation, but there's this additional factor. And there's this lemma we have. The small L2-1 is isometric to large L2-1, and the proof is by using Parseval's identity and some additional argument for this second condition. And using this small L2-1 space, we could define another representation for large L2-1. Because small L2-1 is isometrically, small L2-1 can be isometrically identified with large L2-1, a representation for small L2-1 is also a representation of large L2-1, and vice versa. So here we define a representation which we call Fourier coefficient representation, and we could also consider this as a representation for large L2-1. Here this representation is defined similarly as previously. This is from the string predicate to sequence of complex numbers such that, and these complex numbers are Fourier coefficients. If we think that this representation is encoding the large L2-1 space, and here in this encoding in this string predicate there are three parameters, n, j, and a. N is as always the precision parameter, and j is the bit of the j's position, and a is the index of Fourier coefficient. And in this Fourier coefficient representation, just as previously, n and j are encoded in binary, while a is encoded in unary. This is to make the modulus of representation linear, and so that this representation has linear modulus of continuity, and this is optimal by Steinberg's lemma. And another reason is that because we encoded in this way so that some other function are polynomial time computable. And one, for example, in this observation, in Fourier representation, this functional is polynomial time computable. This is just a matter of there's no much calculation involved, just as an index use this a to be 0 and just read out the information. And this calculating the Fourier coefficient, this can be considered another characterization. A representation delta is polynomial time reducible to Fourier coefficient representation if and only if delta makes polytime computable. This functional that depends on both of f and k, the k is that mapping this to this case Fourier coefficient. And with respect to this Fourier coefficient representation, we conjecture that the functional is not polynomial time but exponential time computable under Fourier coefficient representation. The functional of integrating from 0 to 1 over 3. The computation will be actually converting back to the piecewise representation, and the non-polynomial time proof will be the perturbation argument. But this is a conjecture and we need to work more on this. And we have another conjecture calculating the functional given f and g. This one is the zeroth coefficient of this pointwise multiplication. Is not polynomial computable but exponential time computable under Fourier coefficient representation. The exponential time computability could be proved by can be computed by convolution, and non-polynomial time proof will be the perturbation argument. So I gave you the introduction to the topic of this research and introduced large L21 space and small L21 space. Finally, we will look into the perspectives of this work. So in this talk, we looked piecewise representations of large L21 and also Fourier coefficient representation is the representation of small L21, but they are actually the same representation because this large L21 and small L21 are isometric and can be identified isometrically. So one representation is representation of another and vice versa. And in their encoding, there are three parameters, n, j, and a. N is the precision parameter and j is the bit position of this output, and a in the piecewise representation it is the index of the piece, and in Fourier coefficient representation it is the index of Fourier coefficient. This is encoded, a is encoded in binary and the other n and j they are encoded in unary. This is to make that they have the optimal modulus of continuity, and also so that some function are polynomial time computable. And we conjecture that these two representations are vastly different. And here in this table, the column corresponds to two different representations and the row corresponds to two different functionals. So with respect to piecewise representation, this functional of calculating the integration from 0 to 1 should not be polynomial time computable because you have to access exponentially many intervals. But with respect to the Fourier coefficient representation, it is just a matter of reading of the first Fourier coefficient, the zeroth Fourier coefficient. And so it will be polynomial time computable. And for this functional, another functional, with respect to piecewise representation, this functional is just a matter of reading of the values in the encoding. But for Fourier coefficient representation, it's not going to be computed so easily, so it will not be polynomial time computable because there is a problem that's polynomial time computable in one representation but not the other, and vice versa. We conclude that these two representations are not polynomial time convertible each other, so they are basically up to polynomial time. They are very different non-equivalent representations. So basically we have to choose the representation that suits our purpose. Thank you very much for listening. This is the summary of this talk. We introduce the piecewise representation of L21 and Fourier coefficient representation of small L21, and we conjecture that these two are not polynomial time equivalent, and one needs to pick one of these two representations depending on his purpose. And for future work, we consider similar to Fourier coefficient representation, but Fourier coefficient representation is based on this basis of the vector space. But we are considering another orthonormal basis. What happens if we consider another orthonormal basis, and which functionals will be computable with respect to another orthonormal basis? And we are also going to consider whether is there a functional that characterizes the piecewise representation like in the Fourier coefficient representation. And also we note that combining representation may make more functionals polynomial time computable, but with respect to operators, they may destroy closure under operations. So this is the end of the talk. Thank you very much for listening, and thank you again.